Today we are going to start digital signal processing, and in that design of filters. We are going to talk about at length about the filters. Actually, it is the most important topic in digital signal processing. Digital filters are the part of every communication system. So it is very important to understand the use of the design of filters and how the filters are used according to the applications. The discussion consists a lot of mathematical concepts, all equations, and it needs a patience to understand the design of filters. So we'll begin with what are the filters, what is filter, the types of filters, and the difference between FIR and IR filters. And here we are going to design a finite impulse response filter. This video will be quite lengthy. Let us begin with what are the filters. Filter. Digital filter is a system that performs mathematical operations on sample, discrete time, signal to reduce or enhance certain aspects of that signal. Okay. We can define more particularly, a filter is essentially a system or network that selectively changes the wave shape, the amplitude frequency or phase frequency characteristic of signal in a desired manner. Okay. In communications, we have a signal in which there could be different frequencies. Sometimes it will be a mixture of 2-3 signals. Deliberately, some frequencies are mixed to utilize the bandwidth of the channel. So at that time, the receiver end, we need such a circuit, such an algorithm that will extract, that will remove the undesired part or separate the two signals based on the frequencies. The types of filters. Basic category of filter is analog filter and digital filter. By the name itself, we can differentiate these two filters. Analog filters and digital filters. It is the basic category of filters. What is mean by analog filter? Name itself suggests that it is the conventional filter. Analog filters is described using linear constant coefficient differential equation. So we have to describe the operation, what happens in the system. And in case of analog filters, that operation of frequency selection is described by using linear constant coefficient differential equation. So it is sum for 0 to n ak d raised to k dtk y of t is equal to sum of this thing bk into d raised to k dtk x of t, differentiation of x of t with respect to a given order, and bk is the coefficient. So here we have ak and bk are filter coefficients. System function. The system function of analog filter is described by using Laplace transform. So h of s is obtained by taking Laplace transform of this. We can rearrange this equation. Okay. So in this case, we have two things. We have x of t. What is x of t? X of t is input and y of t is the output of analog filter. And the ratio of these two, when we take ratio of output, so it is output divided by input. So this is nothing but the transfer function, so h of s. H of s is equal to y of s divided by x of s. So it is the ratio of two quantities. So this one is x of t input and it is output. So it gives us the transfer function of analog filter using Laplace transform. An analog filter is implemented using resistors, capacitors, and inductors. As it is analog, the input all this passive electrical components is x of t. And this x of t having with different frequencies These are the reactive components. Capacitors and inductors are reactive components. The frequencies involved and the reactance of these capacitors and inductors changes according to the frequency applied to these components, and accordingly it selects the frequencies and we get the particular frequencies at the output. Accordingly, the analog filters are designed. Now, we have classified digital filters as FIR filter and FIR filter. IIR filter stands for Infinite Impulse Response, and it is the Finite Impulse Response. When we apply an impulse function to a system, to a digital filter, at that time we get some response when input is an impulse. So that is called as a finite impulse response or infinite impulse response. So what is the impulse response is remaining? If it is for finite duration, it is called the finite impulse response. If it is for infinite duration, 0 to infinity, it is called as infinite impulse response. So we have some comparative points for IR and FIR. It will be clear that what is the exact difference between these two filters and what are the nature of these two filters. IIR filter is described using difference equation. Both the filters are described using difference equations. Okay, as the input is x of n. So in both the filters are digital, the input is a discrete input sequence and we get the discrete output sequence. So IR filter is described using difference equation, not differential. Analog filters are described using differential constant coefficient differential equation. So these are the constant coefficient, linear constant coefficient difference equation. So y of n is equal to minus sum over k is equal to n, sum of this ak, and it is y of n minus k. Okay, so this is plus k sum of bkx of n minus k should be k here. So it is k equal to 0 to m, sum over 0 to m bkx of n minus k. It means if you change the values of k here, you will get the complete expansion of this equation, and in that it will be clear that this output depends upon these terms and these terms. Okay, so presence of y indicates that the output depends upon the past output. Okay, so let us take example. Second point and the first point, okay, it will clear what type of filter it is. So IIR is a recursive filter. The filter whose output depends upon the present input, the past input, and the past output. So this is the worth remembering point in case of IR filter. So IR filter uses feedback. Okay, we can take as an example. So when you write y of n is equal to, so it is y of n minus 1 plus 0.5 x of n. Okay, if you put n equal to 0, in this case you will get y of 0 is equal to y of 0 minus 1 is minus 1 plus 0.5, so it is x of 0. We know that, so when we substitute n equal to 0, we get y of 0. It means for present value of index we get present output. This present output depends upon the past. Y of minus 1 is the past output, and this one is what? Present input, x of n, and x of 0 is present output in this context for n equal to 0. Okay, therefore IR filters are recursive filters. The present output is determined by the present input, past input, and past output as well. FIR filter is described using difference equation y of n equal to sum of bkx of n minus k. Okay, so here it should be k. So k is equal to sum of this term or 0 to m. We can change the values of k in this. So no y term is involved here. It means this filter is non-recursive filter. What is the meaning of non-recursive? It means the output depends on present input and the past input only. FIR design do not use feedback. We can take as an example, we can write Now, the simple form of this difference equation is that y of n is equal to, when you write 0.5 x of n minus 0.5 x of n minus 1, you can take plus 0.5 x of n minus 1, n minus 2, you can take anything. When you substitute n equal to 0, we get y of 0, present output. So it is 0.5 x of 0 minus 0.5 x of minus 1. Okay. The present output depends on the present input. This is the present input and this is the past input, x of minus 1. With this context of n equal to 0 is the past input. So no output is involved because feedback is not used in case of FIR filter. The next important point is that IR is non-causal and not guaranteed its stability. IR is non-causal. Okay. FIR is causal and always stable. We'll see when we study the design, we have to make a causal impulse response to make the filter realizable, and we are going to do that. It is non-linear phase frequency response. Okay, it has non-linear phase frequency response and always linear phase frequency response in case of FIR filter. And here the advantage of FIR filter is that it has less number of filter coefficient. Okay, and here more number of filter coefficients and complex procedure for realization. So what's the disadvantage in case of FIR filter? That n, okay, the order of filter is higher and the coefficients are more. Therefore, the procedure of implementation or realization becomes complex and costly. As there are more number of coefficients, it takes the more cost. So let us start the basic types of filters depending on frequency. Okay, x of n is a sequence and it is made of different frequencies. Different frequencies are there. So what we have to do, we want some low frequencies at the output. Sometimes we want high frequencies sometimes at the output. We need some band of frequencies. Suppose we need some band of frequencies sometimes at the output, band of frequencies. And sometimes we need to stop some band, stop some range of frequencies. Range of frequencies need to stop. So for these requirements, we have the types of filters. It is not the basic category of classification. Okay, so all these filters can be IR and can be FIR filters. Okay, so let us understand how these filters are classified or how filters select the network and the name is given to according to that. Okay, so ideal low pass filter. So in this case, this is the omega axis. This is omega axis, and it is the range of this is minus pi to pi. Okay, we can say 0 to pi also. So 0 to 180 degree in degrees, and radius it is in radians. It is omega is 0 to pi. Okay, and in degrees omega is 0 to 180 degree. So here representation of this frequency axis is omega radians, and it is hd of e raised to j omega. What is hd of e raised to j omega? It is the desired frequency response. So d is used to denote something desired frequency response of the filter. Okay, and when we write like this hd of e raised to j omega, so it is read as magnitude of desired frequency response. So it is magnitude of desired frequency response. So here in this case, the low frequencies are allowed. How to identify the filter is allowing the low frequencies? It is, see, the low frequency filter, low pass filter can be shown like this also. Okay, 0 to omega c. Okay, so it allows the filter. It is a standard representation for ideal low pass filter. So why we are getting this edge sharp? Okay, so here the value is 1. HD of e raised to j omega is 1. So we can define this in terms. We can define ideal low pass filter as magnitude of HD of e raised to j omega is, it is 1. So 1 is shown here. 1. When we can get 1. So for some frequency range, we get this. So it is minus omega c to omega c plus omega c. So in this range, we are getting this output. The magnitude of this frequency response is 1. Now in second case, it is ideal high pass filter. Ideal high pass filter can be shown like this. Simply, we can show like this. So, but for negative frequencies also it is shown here. So it doesn't make any difference. So we can define this high frequency filter as magnitude of HD of e raised to j omega. So it will be 1 for, so it is mod of omega c less than pi. Mod means it is plus minus omega c. So it is 1. And it is 0 for rest of the things. Otherwise it is 0. So it is ideal high pass filter. Remember this equation. So we have to take this as a reference when designing the different types of filters. We are going to design ideal low pass FIR filter, ideal high pass filter, ideal band pass FIR filter, and ideal band stop FIR filter. Third case is ideal band pass filter. So band pass means the range of frequencies, it's omega 1 to omega 2. We are getting the magnitude of desired frequency response is 1. So we can write this as, we can define this mathematically, HD of e raised to j omega. So it is 1 clearly for omega 1 to omega 2. Otherwise it is 0. So it is the mathematical definition of ideal band pass filter. Now, fourth one is ideal stop band filter. Ideal stop band filter is, it means during this period, we don't have amplitude, okay, for this desired frequency response. So it is defined as HD of e raised to j omega. It is equal to 1. It is equal to 1 or it is minus omega 1 to plus omega 1. This case. So it is minus omega 1 to plus omega 1. We are getting 1 magnitude response equal to 1. Now again we are getting 1. So it is omega 2 to pi. So it is omega 2 to pi. We are getting 1. So here we are getting 1. Okay, and otherwise it is 0. Okay, for these frequencies it is getting 1, and rest of the frequencies it is getting 0. It means we have to stop other frequencies. Okay, so this is the desired thing in case of band stop filter. Okay, let us take a look at the frequency characteristic of low pass filter. What actually it consists. That is the ideal case. And here have some practical look or how a frequency response looks. Practical filter produce the frequency response and it is like this. In previous case, what kind of frequency responses we have? We have this one here and it is coming sharp to the 0. It is going to 0. So this is called ideal case. It never happens practically. Okay. Practically, it takes some time. When this magnitude response is 1 here, and here it goes to 0. Okay. So here it takes some time. This time is called as a transition time. Okay. Ideal thing never exists. Practically, there is a transition. It monotonically decreases to 0, from 1 to 0. Now we have to represent this in terms of the standard notations. See, this band is called the ripple. So this is the ripple present. So it is tau1 is the pass band ripple. Some kind of ripple is present here. And in tau2, it is a stop band ripple. So this one is the stop band ripple. And here, what is omega? Omega is the ideal pass band cutoff frequency. So we are going to define this pass band, and this one, okay, I'll take different color. So this band, this band is called as the pass band. So this band, here in this band, so this is the pass band of filter. And this one is stop band, transition band. So it is taking some time to set up the filter transition band. The filter want to stop the high frequency. These are the low frequencies. 0 to omega p are the low frequencies. For low frequencies, we are getting the output, and this is the magnitude of frequency response. But as frequency increases from omega p to omega s, it goes to pi, this magnitude of frequency response monotonically goes to 0. Okay, and this is called as a stop band. The filter don't want to allow these frequencies, so it is stop band of the filter. But in stop band, we are getting some values. Okay, so it is called as the stop band ripple value. Okay, and here it's omega s is the stop band. Omega s, what is the pass band? 0 to omega p is the pass band frequencies, and omega p to omega s is the transition band. What is the stop band range? Omega s to pi is the stop band frequencies. The filter don't allow the frequencies in this. Okay, so let us define these standard notations. So it is ideal pass band cutoff frequency omega p. It is the frequency below which the magnitude response does not fall below 3 dB. Okay, we have this kind of magnitude response. Okay, and this is 1. Okay, and this is 0 to omega p. So here the cutoff starts. It's ideal cutoff, and here it monotonically decreases of the magnitude response of the frequency response. Okay, so it is the frequency below which magnitude response does not fall below 3 dB. So this is the 3 dB frequency in terms of decibel. Okay, and the magnitude response, magnitude of HD of e raised to j omega varies between 1 plus minus tau1. Okay, 1 plus minus tau1 means what? So we have this kind of frequency response. So it goes like this. So here, this is called 1 plus tau1 and 1 minus tau1. So it is the 1 plus minus tau1 during the 0 to omega p. So this happens during 0 to omega p. Okay, and it is called the ideal pass band cutoff frequencies. It's a pass band of the filter. Tau1 is the ripple in pass band, and it is calculated as 20 log to the base 10 of tau1. So it is converted into decibel band. Transition region. What is the transition region in the frequency characteristic of filter? The region between omega p and omega s, we had this region. Okay, we'll draw here. So we have this ripple, and then it goes to this one, and here stop band ripple. So this region is marked between omega p and omega s. So this region is called as transition region. Okay, the region between omega p and omega s is transition region, and in transition region, magnitude frequency response was by 60 dB. Narrower the transition region, better is the rejection of unwanted frequencies. Okay, what is the ideal case of filter? The ideally the filter should be like this. Okay, so it is the omega p. So below which the frequency response is getting, and above these frequency values, we are not getting anything. Okay, so this is the ideal case. So as this width of transition region decreases, we approaches the ideal case. Okay, so this transition region should be narrower and narrower, and better is the rejection of unwanted frequencies. Okay, so here some frequencies are allowing into the output. Therefore, we are getting such kind of monotonous decrease in the K. The design to design filter with sharp cutoff needs more hardware and high cost. Okay, so this is the relation between the width of transition region and the cost of the design of the filter. Now, necessary and sufficient conditions for the design of positive filter. So we have this ideal low pass frequency response. Okay, HD of e raised to j omega is 1 for magnitude of mod of omega to mod of omega c. Okay, so this value we are getting 1, and 0 to pi, this omega c to pi, sorry, it is getting 0. So we are here output is 0 here. Okay, so this is the first case, ideal low pass. So we should know this to understand the design of filter. The impulse response of filter. Okay, what is the impulse response of the filter? When we apply impulse as an input to a filter, okay, so we have some impulse response. At that time, we get output y of n, and we have some impulse response h of n. Okay, so the system's response to an impulse input is called impulse response on the system, impulse response of the filter. And impulse response of the filter is defined. We are getting this kind of impulse response. Okay, this one. So this was sine and this decreasing. Okay, so slowly it is going to 0. It decaying on the both sides of 0, and it is defined by using h of n equal to omega c divided by pi. So this portion is omega c divided by pi. For omega, mod of magnitude of mod of omega is less than mod of omega c. So this range of frequency is defined this portion using this omega c by pi. Now rest of the portion on both sides is defined by using omega c to sine of omega cn divided by pi omega cn. Okay, omega c to pi on both sides. So it is omega c to pi on both sides. So it is monotonically, or we can say exponentially, it is going to 0 on both sides. Okay, we consider left half of this portion because we consider the negative frequencies in the design of the filters. Okay, the impulse response is not symmetrical. The first important point, that is our observation, that the impulse response is not symmetrical. Okay, because it is going to infinity. So it is unstable. Okay, it is not symmetrical. What is the condition for a system to be stable? So we have studied that h of n, okay, 0 to infinity, okay, should be less than, sorry, it's not in integration because it is discrete signal. In case of integration, we can use integration. So it is 0 to infinity, or we can say minus infinity to plus infinity. H of n should be less than infinity. Then the system is stable. So it is not satisfying this condition. It is unstable because it is not summable. It becomes unrealizable. The third important point is that with such an impulse response, which is not summable, it is not stable, and the system becomes very difficult to realize. Okay, so it becomes unrealizable. Practically, we cannot implement it. Okay. Now there are some conditions. What we have to do there? Okay. So we have to truncate this. We have to truncate. It is called truncation. Okay. we have to truncate the impulse response. We have to take some conditions and we have to design the filter. If h of n has finite energy, okay, we have seen that it has a finite energy. It is going to infinity, and therefore then h of n equal to 0. Okay, so here it is infinite. If h of n equal to 0 for n is less than 0, okay, for n it is n and it is n less than 0. Okay, if it is 0, h of n is 0, impulse response becomes 0. Then we have integration of log of impulse response will become the less than infinity. Okay, then resulting filter with frequency response is causal. Okay, when we do this condition, the filter becomes causal. Okay, so it is called polylinear theorem. Okay, h of e raised to j omega is equal to magnitude of h of e raised to j omega into e raised to j phi of omega. It's just a condition, you should know about it. Okay. Now, what are the filter design methods in case of FIR filter? First is Fourier series expansion method. Second is windowing method, and frequency sampling method, and computer-aided design method. So we are going to study first this method and second windowing method. Now see what happens when you study windowing method without studying this Fourier series expansion method. You will not understand what is the importance of windowing. Okay, because here you will come to know the difficulties in the design of filters, truncation of impulse response, obtaining the coefficients and plotting the magnitude of frequency response versus omega. Okay, and here by using window, you are selecting some part of this and you are designing the FIR filter. Okay, so we have first method, Fourier series expansion method of design of FIR filter. So we are designing FIR filter using Fourier series expansion method. Okay, so here are some design steps. I didn't write the exact steps, but here some basic equation I have written, then simplified version of equation I have written. So how we have obtained equation, you will come to know from this discussion. So frequency response of FIR filter written in terms of Fourier series as ht of e raised to j omega is this one. Okay, ht of n e raised to minus j omega n. Where ht of n is the notation d stands for desired impulse response. Okay, taking inverse Fourier transform of this, we get ht of n is equal to 1 or 2 pi integration of ht of e raised to j omega e raised to plus j omega n or minus pi to pi. Okay, now in inverse Z transform of equation 1, okay, we have this equation 1. So this equation 1, when we do inverse Z transform of this, so we can obtain the transfer function of FIR filter. So this one is transfer function of FIR filter. Okay, so it is sum of ht of n z raised to minus n or n equal to minus infinity to plus infinity. Okay, making h of z as an approximate from infinite impulse response. What is the difficulty here? The sum is for n equal to minus infinity to plus infinity. Okay, this is the difficulty. So this thing is not realizable. So we have to truncate this. Now, what is the truncation approach? Making h of z as an approximate from infinite impulse response. Okay, so this is the important step in the design of realizable FIR filter. So what we are doing, we are taking h of n equal to hd of n. We have hd of n here, and for magnitude of n equal to n should be less than n minus 2, n minus 1 by 2. Okay, and mod of n should be greater than minus of n minus 1 by 2. Okay, here you will not understand what exactly is going on. Okay, when we'll design the example of ideal low pass FIR filter, at that time you'll know what is mean by this step. So h of z becomes, now if you substitute this into h of z equation, h of z, we have now written transfer function in terms of z transform. So h of z becomes this one. Okay, and the final equation is this one. So here It's not final equation we are going to design the filter, but h of z equal to h of 0, n equal to 1 to sum of these things or n minus 1 by 2, 1 to n minus 1 by 2. And this is the h of n, z raised to minus n, h of minus n, z raised to plus n. Now, impulse response is symmetrical at n equal to 0. Then we have to obtain the impulse response. H of n equal to h of minus n. Okay, we'll obtain by using this relation. Equation 4 modifies to. Now this will change. H of n equal to h of minus n. So this equation will modify to h of z equal to h of 0. Already we have h of 0 here, and it will become h of n will take common, and z raised to minus n plus z raised to plus n. So this is equation 1. This is equation 5. The transfer function is not realizable yet. Okay, so we cannot realize this transfer function. Okay, what we have to do now? We have to delete this transfer function. Okay, when we multiply this transfer function using the whole term is multiplied using z raised to minus 1 n minus 1 by 2. Okay, what is n minus 1 by 2? Suppose n is equal to 11. Okay, so this term will become z raised to minus 11 minus 1 or 2. So this will become z raised to 10 divided by 2. So this will become z raised to minus 5. Okay, so it is the whole transfer function, equation 5, right hand side is multiplied by this equation. Now each term will be delayed by using z raised to minus n minus 1 by 2. Okay, I'm going to erase this rough work. Now see, just by multiplying with the delete function, let us call this as h of z, h dash of z. Okay, so this is the h dash of z. The new transfer function is h dash of z is equal to z raised to minus n minus 1 by 2 into the whole transfer function h of z. We have this h of z, complete h of z we have written here. So h of 0 plus sum of h of n z raised to minus n plus z raised to plus n over 1 to n minus 1 by 2. Okay, if it is n equal to 11, it will be 11 minus 1 by 2. It means it is 10 by 2 means 5. So 1 to 5 h of n z raised to minus n plus z raised to plus n. Okay, we have to, while finding h dash of z, we have to multiply these terms first, and then we have to multiply each term in this bracket by using z raised to this number. Okay, then we'll obtain the transfer function. Now we have to obtain the one more transfer function h dash of e raised to j omega. Okay, we can write new coefficients and new frequency response as h bar of e raised to j omega. Just a notation: a0 plus n equal to 1 to n minus 1 by 2 sum of an cos omega n. So this is the Fourier series expansion approach. Now here we have two things, a0 and an. How to obtain the value of a0 and an? So here this an is calculated by using an is equal to 2h of n minus 1 by 2 minus n. For example, suppose n is 11, so we'll get 2h of 11 minus 1 by 2. So it is minus n. Okay, you are finding, sorry, it is the formula for an. So I have shown for a0. Okay, so this is for a0, h of n minus 1. So it is if n equal to 11, suppose n equal to 11. So this will become a0 is equal to h of 11 minus 1 by 2. So it is h of 5. The value of a0 will be h of 5, like this. And here, so an is calculated. Suppose n equal to 1, suppose n equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 5, and put the values of n. N minus 1, we have n is equal to 11, suppose, and then we can obtain the a1 to a5, a0 to a6 value. Okay, and we can substitute in this equation. Now, the last step in the design of FIR filter is you have to substitute the value of omega. Okay, substitute the value of omega. Okay, substitute each value. Okay, so this equation will become so omega. So this is not omega. So putting the values of different omegas. So let us elaborate this equation. A0. So it is A1 cos of omega 0n plus A2 cos of 2 omega. So it is 1 omega, this one, plus A3 cos of 3 omega plus A4 cos of 4 omega and 5 omega, so on. So we have to obtain the values of omega, and we have to substitute 1 omega, 2 omega, 3 omega, 4 omega, and 5 omega, and so on. So what we have to substitute in place of omega? So we have to substitute omega is equal to 0 first, then find the h bar of e raised to j omega. Then substitute omega equal to 10 degree. We are putting in degrees. And then h bar of e raised to j omega. You have to find the magnitude of this by putting these values. Put omega equal to 20 degree and up to omega is equal to 180 degree. We can substitute and find the values. And then we can plot the graph. We can plot the graph of frequency response h bar of e raised to j omega versus omega. Okay, we'll get some graph here and we can obtain the ripple for pass band and the stop band. Okay, so in the next video we are going to design the ideal low pass FIR filter by using Fourier series expansion method.